Okay, so let's look at the economics now. All right, so what we're looking at here is just where you might get the most bang for your buck. This is in 7.8, but let me just read a little bit from 7.7 before we get too far ahead of ourselves. So, things to consider: annual energy production from the wind turbine installation. So this is thinking back to summary 4. How much energy are you going to get over the long haul? The next thing that's mentioned is capital costs of the installation. So that's your initial price. What do you have to do to put into it? Obviously, any of these offshore, it's going to be more expensive. You're out in the water, you're putting footers in, dealing with waves, maybe some underwater welding involved, very expensive. The next thing that's mentioned, it says the discount rate being applied to the capital cost of the project. And this says, see Chapter 10 and Appendix B. I'm gonna just go ahead and take a look at Appendix B. Yeah. And the most, I'm just going to hold this little table up. I'm looking at Table B1 at the end of the chapter, and what we're looking at is the discount rate or the interest rate. So if, let's just take a look here. Okay, annual repayment in pounds per 1,000 pounds of capital. And I'll just throw a couple numbers out there as I'm reading through this. So the economics, and I'll just do a couple little cells. So this is how much time you have to pay it back: 5 years, 10 years, on down the line up to 60 years. And we're looking at, and I'm going to just write it as $1,000. Let's just say somebody gives you $1,000 now, and you've got a certain amount of time to pay it back. Now, the percentage, let's say if you've got a 0% interest rate, someone gives you $1,000, 1,000 divided by 5 is 200. So let's just say your wind turbine costs you $1,000, and you're going to make a certain amount of electricity from it. And let's just say, for the sake of argument, that you're going to make $200 worth of electricity per year. After 5 years and 0 interest, the rest is gravy. But let's just say somebody wants to charge you 2% interest instead of 0%. You're going to have to pay them back $212 per year, and it's going to take you longer to get to the gravy point. If we come all the way out here to 15%, and you've got 5 years to pay it back, you're going to need to be coughing up $298 per year.
For 5 years.
Yes, for 5 years, exactly. Now let's go to the bottom. I just want to fill out the rest of the table. 1,000, if you've got 60 years to pay it back, you're going to pay $17 a year. Let's just verify that. So, and that's at a 0% rate. So 1,000 divided by 60 years equals $17 a year. Okay. And then if you are, if you've got a 15% rate, you're going to be paying $150 a year for 60 years. Yeah. So that's the cost of money. Money is not free. People who, and the reason is because things become more expensive. A dollar now is going to not be $1 tomorrow because of inflation, just the way it works. Okay, there's a little, a little bit on economics. Now, now we're into 7.8. And we're looking at figure 735 on page 337. And they've sort of separated these into different categories. The blues are all round one offshore projects that are operational. So all these guys out here are running. The yellows have been approved. There's a few that have been approved. And then the whites, there's a couple of them here, have been submitted. And then here's another round two. The land-based in green, they're not listed as either being operational or permitted, but obviously plenty of land-based wind turbines in the UK. Okay. Now, the next one is table 7.2, and I'm just going to take a look at it. Here it says, the breakdown of global wind power capacity. So Europe, Germany leads, Spain is next, Italy, France, the UK, on down the line. In Latin America, Brazil is the top with 600 megawatts of capacity. It also shows how this has grown. So just in the year of 2010, when this was written, Germany went from 25.7 gigawatts to 27.2. In North America, and this is pretty impressive. I'm seeing the U.S. at 35 gigawatts, heading all the way up to 40 just in 1 year, and that's more than any other country. Now, China, on the other hand, started the year at 25 and finished up at 42. So it looks like 2010 was the year that China surpassed the United States in wind power. Kind of cool to see that there. It'd be interesting to see where we are down the road. But. Okay. Egypt, a little bit. Morocco, a little bit. Others, not so much going on in Africa or the Middle East. And the total power was 158 gigawatts at the beginning and 194 gigawatts at the end. Let's just see what the capacity is right now, 5 years later. So 51 megawatts, according to this Global Wind Energy Council. New record in 2014. Globally, 51 gigawatts was added. So the world in 1 year added a quarter of what was on the planet in 2010. So yeah, it's pretty impressive. And it says the total stands at 370 gigawatts, which is almost double what it was in 2010. So in 5 years, so from time 0 to 2010, we got 194, and from 2010 to now, we're already at knocking on 400. So pretty impressive. All right, so here's a small scale turbine. Looks a lot like the one we own. Might be 5-10 kilowatts. Larger. This is what they're calling a wind farm cooperative. So not unlike the solar cooperative that you visited today, where a lot of people put in some investment, each little person in this co-op owns a small portion of it, so, pooled funds, and then the electricity comes back over time. I love seeing these. This looks like a neat way to get some energy tech directly on the building, and I think what they're trying to show here is you could actually have yeah, exactly, yeah. You've got sun where you need it, you've got wind kind of sitting down there in the shade, and you have this shape of your building that's more or less funneling air into the technology. All right. Okay. I like table 7.3. Let's take a look at table 7.3. Because a lot of people say, well, gosh, is there enough renewable energy out there blowing around, bubbling up, what have you, on the planet to satisfy global demand? And I think the answer is yes. So let's just look at that here. This is table 7.3. And I'm just going to look at the global numbers. So demand in 2025 is going to equal 26,000 terawatt hours. Now let's convert terawatt hours to megajoules. Okay, so let's start here. So 26,000 terawatt hours. 26,000. Control 1. Number. Dink, dink, dink. And let's do it this way. Let's put it in kilowatt hours. I like to get into a comfort zone, and let's put this into megajoules. So one kilowatt hour equals 3.6 megajoules. I'll just verify that. One kilowatt hour, 3.6 megajoules. I don't know why they split this in area. It's funny. There we go. So 1 kilowatt hour, 3.6 megajoules. So all I've done here is said that this number equals that number times 3.6. Okay, but the kilowatt hours equals this number. So kilo to mega is 3, to giga is 6, to tera is 9. So equals that number times 1E9. So there's kilowatt hours. There's megajoules in scientific notation. Copy, paste, equals that number. Ding. I'm going to change this to engineering notation. So control 1. I think it's under special. No, custom. Here we go. Okay. So, right. So now we've got it in megajoules. So 93 trillion megajoules. So now let's go ahead and just take megajoules and convert it to exajoules, because for global energy total. So exajoules equals, so now to go from mega, which is to the 6th, exa, which is the 18th, we need to divide that by 12. Equals that, divided by 1E12. Now we can just go back to number. Okay, cool. That's exactly what I want to do. So, again, to remind us where we are looking at page 343, table 7.3, and what we're seeing is that the world demand for electricity by 2025 is 26,000 terawatt hours. We converted that to kilowatt hours. We converted kilowatt hours to megajoules. We converted megajoules in scientific notation to engineering notation, and then finally converted megajoules to exajoules. 93. So what that says is that of our 500 exajoule budget, about 20% of it is electricity. Now, the other news is that our wind resource could be as high, and this is a little bit difficult to interpret, but I see 70,000, I see 185,000, I see 335,000. This is the total capacity, and so I'll just write those in here too. Capacity, so 70,000. I'll call this cap 4. Cap 3. So this is 185,000, 335, 400.
That's 70,000 gigawatts.
Oh, you're right, isn't it? Yeah. Okay, let's just skip that one. Thanks. I'm going to take these cells, copy them, paste them, paste them. Okay, so what I'm seeing here, so I just took those cells that we took a lot of time to calculate and just copied them for the same capacities for wind resources. So what I'm seeing here is that if you combine this class 4 sites and the class 3 sites, there's enough wind to supply all of the planet's energy. And then some, yeah. So we're not really short on resources, we're just kind of short on innovation and willpower. Okay, cool, that's good news. All right, well, that's a good note to end on. We'll get back into the rest of the chapter on Tuesday. I'll fold the page, so we'll start on 344.
Well, I can write it down.
Thanks.
Oh, I'm digging the time change at the moment.
I'm not either. It's a drag. It's not going to get any better either.
I wasn't ready for the early sunset. I like the summer skies.
Yeah, me too.
So I'm thinking I'm going to use my daughter and turn